So we just discussed about perfect binary trees. Remember, these are trees, binary trees, where every non-leaf node has exactly two children. As a result of which, we can have one node, for example, for one level, we can have three nodes in a two-level tree because the root then have two children. We can have seven nodes in a three-level tree, so root has two children. Those two children again have two children. So one, two, and four, seven nodes. 15 nodes for four levels, 31 nodes for five levels, and so on. Basically, it's always of the form 2 to the power of n minus 1, where n is the number of levels. The question that comes up is what happens if the number of nodes in their binary tree is not one of these? For example, let's say I want to have a tree with, let's say, 12 nodes, or perhaps I want to have a tree with, let's say, maybe 9 nodes, or say maybe 6 nodes, something like that, which is not in one of, let's say, these numbers. Now, clearly, we cannot form a perfect tree in that situation. However, we can still form a binary tree. In fact, there are many, many possibilities to form this, but we are going to follow a rule, a very, very specific rule, which is that on the last level, we are going to fill this tree from left to right. Now, why are we doing this? Well, because this rule leads us to what is called a complete tree, and heaps are basically complete trees, right? So by following this rule, we are ensuring that we are in the right structure that is suitable for heaps. This will obviously become more clear as we go on, but for now, let's look at some examples to understand what this rule is. So let's say we had a situation where we had 12 nodes. Now, clearly, this is going to require four levels because look, 12 is more than 7. So we can't do it in three levels. At the same time, 12 is less than 15, which means the fourth level will be formed. However, the fourth level cannot be complete. But like I said, in order to meet the completeness property, the so-called complete tree, we are going to fill the fourth level from left to right. So notice in this example, for instance, I've got five children, five nodes on the on the last level. In a perfect tree, there were eight children, which means that there are many, many ways to place the five out of these eight. However, the specific rule we are following here is to say that, okay, look, I'll fill this from left to right, as a result of which this node here will have two children, this node will have two children, this node here will have only one child, and that is the left child. And as a consequence, this node here will have no children whatsoever. So notice we are filled from left to right. And the last level hence looks more biased towards the left, right? Or more, let's say, occupied towards the left. And this is what is called a complete tree. Again, heaps are complete trees, and the rationale for all of this will become more clear as we go on. Let's take a look at some more examples. Let's say we have nine nodes. So I'm going to fill. Basically, I need four levels again. So first root has two children. These two children have two children each, so that is seven nodes in all. Now I've got two nodes to place here. These go on the leftmost, let's say, node here. These become children of this node. These two become the children of, let's say, this node over here, because remember we are filling from left to right. Once again, just for illustration, I could very well have placed this, let's say, these two to be children of this node. That will still be a binary tree, but that will not be a complete binary tree. That's not what we are interested in. We are following this rule that we are going to go from left to right, and that's how the tree will be drawn, right? So basically filling from left to right, this is nine nodes. If I had six nodes, for instance, so I could have done, let's say, one root has two children. These two children, this has two children, this has only one child, only the left child, because once again, I'm filling from left to right in order to remain so-called complete, right? Now, really, there's a lot of terminology in this, which can be very confusing, but let's just make it very simple. We are always going to keep it filled from left to right in case the level is incomplete. If the level is complete anyway, it becomes a perfect tree. So if you think about it, all perfect trees are in fact also complete, because all that's happening, for example, in here, here, so I'm filling from left to right. It just so happens that I complete the entire level. That's called a perfect tree. On the other hand, all complete trees are clearly not perfect, right? So this tree is complete, but this is not perfect. Given this, in fact, if we call a tree as a complete tree, that is sufficient, because that also covers the case of perfect trees. And as we'll see later on, heaps are basically complete binary trees. So fill from top to bottom, left to right. And this is what we are going to see in the next video, where we'll see how we can impose this structure that we have been developing onto a list and how does it all work out. I hope you found this interesting. Do look at our website www.whitebyte.in for more such material, and forever enjoy coding. Take care. Thank you so much. Bye bye.